Hello everyone, my name is Uzam Haider and today I am going to present my thesis on the topic Design and Development of a Prototype GUI-based 4-wheel independent steering control RoboCar. This project was supervised by Engineer Dr. Abdul Aziz Memon at Sakhar IVA University. Over the next few minutes, I will take you through the various aspects of my research and development process, highlighting the significance, methodology, and outcomes of this project. Here is the outline of my presentation. We will start with the problem statement, followed by an introduction, a review of existing literature, the objectives of my project, the methodology used, the features of the developed system, a projection of its autonomous driving capabilities. Let's begin with the problem statement. The current educational platforms for land vehicles primarily focus on self-driving capabilities, but often overlook the critical functionality of 4-wheel independent control. This advanced control mechanism is essential for performing complex maneuvers and enhancing vehicle stability. However, there is a notable lack of educational resources that provide students with hands-on experience in mastering this technology. This project aims to bridge this gap by developing a versatile, cost-effective, real-time solution suitable for research and educational purposes. Let's head to the introduction. Land vehicles have seen significant advancements in transportation technology over the years. Traditional two-wheel steering mechanisms have inherent limitations in terms of maneuvers and time efficiency. With the rapid development in vehicle technology, 4-wheel independent driving systems have emerged, offering more stable and precise driving capabilities. These systems are particularly advantageous for performing complex maneuvers, which are essential for advanced autonomous navigation. This project focuses on developing an educational tool that enables hands-on learning of 4-wheel independent control, providing students with practical experience and a deeper understanding of vehicle dynamics. Now let's delve into the difference between two-wheel Ackermann and front-wheel Ackermann steering mechanisms. You can clearly see like this two-wheel Ackermann mechanism uses a simplified geometry for steering two wheels. It improves turning angles for stability and is commonly used in low-speed vehicles such as carts and forklifts. The main advantage of this two-wheel differential is its simplicity and ease of implementation. Now if you see on the other side the front wheel Ackermann, in this system both front wheels steer at different angles to improve control and maneuver. This mechanism is widely used in passenger cars and race cars that we daily use because it allows for sharper turns and better handling at higher speeds. The angles are calculated to ensure that all wheels have a common turning point, reducing the tire wear and improving stability during turns. Now let's head to the 4-wheel independent steering control. The 4-wheel independent steering control system allows for complex maneuvers essential for advanced autonomous navigation. This type of steering mechanism can perform operations such as diagonal movement and crab walking, significantly enhancing the vehicle's versatility and maneuver. This system enables the vehicle to move laterally without changing its orientation, providing a unique advantage in navigating tight spaces and executing precise movements. You can clearly see in this figure that there are different modes of four-wheel independent steering control. So our project RoboCar incorporates this advanced steering mechanism, offering students a comprehensive learning experience in vehicle control systems. So let's see the literature review. The keyboard. This utilizes a two-wheel differential steering mechanism, which is relatively simple but limited in maneuver. It designed primarily for educational purposes, focusing on basic principles of robotics and autonomous driving. However, its limited steering capabilities restrict its application in advanced vehicle dynamic studies. Next is the MIT race car. It employs front wheel Ackermann steering, providing better control but still lacking in advanced maneuvers. This platform is used in educational settings to teach students about autonomous navigation and control algorithms. It uses a front wheel Ackermann steering, which makes it suitable for higher speed applications. Next is F110. It also uses the front wheel Ackermann steering, offering stability but limited advanced control capabilities. Again, it uses front wheel Ackermann. It focuses on speed and stability, but it doesn't provide the flexibility needed for complex maneuvers, which we really want to achieve. Next is the CNN-based scale vehicle, developed in 2020. It utilizes front wheel Ackermann steering, focuses on machine learning for navigation, but not on advanced steering control. This vehicle is designed to showcase the capabilities of convolutional neural networks in autonomous driving, but its steering mechanism limits its ability to perform complex maneuvers. Next is the Jet Racer and the Jet Racer 4WS. Both use independent four-wheel Ackermann steering, providing advanced control and maneuver. These platforms are designed for high-performance applications such as autonomous racing and advanced navigation. They offer a high level of control, making them suitable for research and educational purposes. However, their cost can be prohibitive for some educational institutions. Now, if you see our RoboCar, it uses independent four-wheel Ackermann steering system controlled by a Raspberry Pi 4 with additional onboard sensors for real-time monitoring. This combination makes our platform unique and valuable for educational purposes, offering a comprehensive learning tool for understanding advanced vehicle dynamics and control systems. It's cost-effective, versatile, and designed specifically to enhance the educational experience by providing hands-on learning opportunities in four-wheel independent control. Now let's see a brief comparison between the Jet Racer 4WS and our RoboCar. Both use independent four-wheel Ackermann steering, providing advanced maneuvers, while the Jet Racer 4WS use a controller for auto-tuning, path following, focuses on ease of use but limiting educational customization, while our RoboCar uses PID steering control with a master-slave control setup, allowing for more customizable and educational programming. This setup enables students to experience with and understand the underlying control algorithms. While the Jet Racer 4WS is powered by an NVIDIA Jetson Nano, offering high computational power but also at a higher cost, while we utilized a Raspberry Pi 4 controller, which is more accessible and cost effective for educational institutions, making it easier for students to replicate and modify the setup. The Jet Racer 4WS costs around $850, while our RoboCar is more affordable and at approximately $300, making it an ideal choice for educational purposes without compromising on functionality and learning potential. So these are the objectives. So the first objective is to develop an educational tool that enables hands-on learning of independent four-wheel control. This includes understanding the mechanics and control algorithms involved in four-wheel steering system, providing students with practical experience and enhancing their knowledge of vehicle dynamics. While the second objective is the real-time monitoring system, and it integrates a GUI-based real-time monitoring system for immediate feedback on vehicle performance and environmental conditions. This features allows for dynamic adjustments and a better learning experience, enabling students to analyze and observe the real-time impacts of the sensors. Now let's see our RoboCar utilizes which type of components. First is the Raspberry Pi 3B Plus. It is the main central controller for the project, running the software and handling sensor data. The Raspberry Pi provides the computational power required for processing sensor data and executing control algorithms. Next is the Raspberry Pi camera. It is used for capturing images and videos which can be processed for object detection and autonomous navigation. Followed by the ultrasonic sensors. These sensors are used for obstacle detection, providing crucial data for autonomous driving navigation. They emit sound waves and measure their return, providing a real-time data to Raspberry Pi. Next, the 3D printed chassis that we have utilized in our project. This chassis provide a lightweight and durable frame for the vehicle. The main material for our project was the acrylic. The 3D printed design allows for customization and easy replication for updation in future of this project. Next is the electric motors. They are used for propulsion and steering. These motors are controlled by the Raspberry Pi through a motor driver. The motors enable precise control of the vehicle's movement. Next is the motor driver. This component controls the speed and direction of the motors based on commands from the Raspberry Pi. The motor driver ensures efficient power utilization to the motors, enabling smooth and controlled movements. Now let's see the circuit diagram of our project. You can clearly see all the components that are connected to the central controller, which is Raspberry Pi. So the Raspberry Pi is connected to the motor driver, which in turn is connected to the electric motors. Ultrasonic sensors are connected to the GPIO pins of the Raspberry Pi for data input, which are crucial for the autonomous navigation and for the calculation of the distances. The camera is connected via the CSI port to the Raspberry Pi. Power is supplied to the Raspberry Pi and motor driver from the battery pack. Detailed wiring ensures a stable and reliable connections for accurate data processing and motor control. Now let's see the output results of our RoboCar. You can clearly see the two functions, the diagonal mode and the crab mode of our RoboCar. The vehicle can, in diagonal mode, the vehicle can move diagonally, allowing for efficient navigation in tight spaces. This mode is particularly useful in scenarios where the vehicle needs to change direction quickly without significant orientation adjustments. So next is the grab mode. The vehicle can move sideways, providing a unique advantage in navigating constrained environments are usually used in parallel parking. This capability is crucial for applications requiring precise lateral movements. I already emphasize that it is very crucial for the utilization in narrow spaces for performing complex maneuvers around the obstacles. So this is the GUI of our RoboCar. All the buttons are given to the user for interacting with all the functions that we have provided, such as grab mode, straight mode, diagonal mode, and a user can easily interact with these buttons to independently control and test and optimize the functionality of the RoboCar. So this is the autonomous car marquee projection. So let's see the software components that we have utilized. We have utilized programming languages and libraries such as Python, and libraries such as OpenCV for imaging processing and Pygame for the GUI. These libraries provide the tools needed to implement complex algorithms and create a user-friendly interface. Some control algorithms for autonomous navigation, followed by the integration of sensors like ultrasonic sensors, camera sensor for decision making, user interface for interaction and programming. So the software integrates data from various sensors, providing a comprehensive understanding of the vehicle's environment. So let's see the future directions. We are planning for the expansion of the kit's capabilities and its features. Also, we are seeking opportunities for further development and enhancement while keeping collaboration with the educational institutions and industry partners. This project will create a long-term impact on STEM education and autonomous systems research. These references include all the sources and research papers we consulted during this project. These resources were crucial in shaping the development and implementation of our RoboCar. They include academic papers on autonomous vehicles, documentation for the Raspberry Pi and its components, and tutorials on software libraries used in the project. So finally, we have a list of websites and online resources that offer valuable information and components used in this project. These websites include official documentation, forums for troubleshooting, and online stores for purchasing hardware components. Well, thank you for your attention. This concludes my presentation on the topic design and development of a GUI-based four-wheel independent control RoboCar. I hope this presentation has provided you with all the comprehensive understanding of the project and its potential impact on autonomous vehicle education. Thank you.